Hey guys, Nick here, and today we're going to take a look at electric fields, voltage/electric potential, and potential energy. Now, the way I'm going to treat this lesson is I'm going to divide it into two sections. I'm going to have the first section be purely conceptual, so we're going to focus on things like which direction does an electric field point, away from or towards this charge? Which direction, left or right, will something get pushed by this field? Rather than the numerical nitty-gritty of it. And then in the second half of the lesson, we will learn the maybe only really two equations that are the quantitative numerical side of it. So you'll be able to calculate exactly how many volts the potential is here and things like that. It does tend to be the first half that confuses people more often, and that's for good reason. This subject is really complicated. There's an absolute insane amount of minus signs to keep track of, but if you think about it in a nice systematic way, which I'll show you, it'll be really easy for you to go back and forth between electric field, potential energy, things like that. This specific way of thinking about it came out of some lectures I gave my Physics 2 students last year, but that being said, there are a lot of ways of thinking about this, and other people might have better explanations. However, if you find this specific way helpful, a lot of my students thought it was rather self-contained. The best thing you would be able to do for this channel, if you enjoyed it, would be to drop it in your class's group chat and help other people out with it. It would be a great way to spread the channel. I would appreciate that. Alternatively, if there are things you think I could improve on this lesson, maybe some specific words that I left out, there often are some key words that get people to click in their understanding, please drop a comment, let me know. These videos are a work in progress, and I will remake them eventually depending on what people's feedback has been, so I really do appreciate all that input. Alright, without further ado, let's get into it then. Alright, so as I mentioned, the first half is going to be the conceptual half. So I'll just write that out here. Conceptual. This will be part one. Okay, and the first thing we're going to touch on is electric charges and forces. So electric charges are obviously positively and negatively charged particles, and whether or not they attract each other, so that whether or not they get pulled towards one another or push each other apart, is told to you by the maybe familiar rule of opposites attract and like charges repel. Opposites attract is probably the one to remember. So, for instance, if I have a positively charged particle and a negatively charged particle, let's say I fix the location of the positively charged particle, so it's sort of pinned in place, it can't move. In response, the negative charge will slide towards it until it gets close to it, at which point it might even hit it, unless we do something about it. If I let them both loose, the positive will get pulled towards the negative, and the negative will get pulled towards the positive. Alternatively, if I have two positive charges, let's say two protons next to one another, each will get pushed away by its partner, and in the exact same way, two electrons will each push each other away from their partner. Again, because they're the same sign charge, they don't like being near each other, they want to get pushed away to get to a more favorable place. Now, what's really interesting and something that isn't really obvious is the principle of superposition. So that would come into play, for example, let's say if I had a positive charge pinned here and a negative charge pinned here and a positive charge sitting in the middle. And let's say I force these guys to sit in place. So I pin them down, and I ask, in response, what happens to the positive charge? Which direction does it move? Does it get pulled towards the positive guy? Does it get shot off in some random direction? What happens to it? the surprising result is that you can actually just consider what would happen to each of these systems separately. So what would the positive charge in the middle do in response to this positive charge? And what would the positive charge do in response to this negative charge? You can ask those questions separately, find out the resulting force, and then simply add the resulting forces together to get the net force. So in this example right here, a positive charge hates being near a positive charge, so it gets pulled that or pushed that way by the positive charge. And now we separately ask, how does it interact with the negative charge? Well, the negative charge would pull it towards it. So the net result is that there is a very strong pull in this diagonally down and to the right direction. So again, this is the principle of superposition. You may also hear this used in quantum mechanics or wave mechanics. It's a very similar idea. You can just add up results. And we will use this later. This seems very clear why this should happen. You just add forces together. But when we get to electric field and things like that, this example will come back and it'll make sense. Okay, now we're going to do a reminder quickly of what potential energy is before we get into electric field and potential, also known as voltage. Now, potential energy, it turns out, is probably the most important thing that you will learn in your time in a physics classroom. A lot of the stuff, including even Newton's laws, you may never use again unless you're an engineer. However, potential energy is something that really is far-reaching. The concept of things wanting to go to low areas of low potential energy really permeates a lot of things. For example, in biology, cells and cellular processes are often driven by this fact that things will fold into configurations that are more energetically favorable. And this ends up driving a lot of things. You can also find examples in, let's say, disease spread modeling and public health. So potential energy really is a key player here. Now, for our purposes in electric field and related things, the key point about potential energy to remember, and it's so important, I'm going to write it in our handy-dandy Galaxy colorway pen, is that potential energy describes where things hate being. And I'm actually going to say positive. I'll say large/positive potential energy describes where things hate being. Okay? This is a phrase. If there's nothing else you take away from Physics 2, this is probably the one to remember. In fact, this probably is the one to take away from Physics 1 as well, because it's just that central. Now, you've probably heard of potential energy in terms of stored energy or energy of position, and that is totally fine. It's a compatible definition with this one. However, it doesn't tell you high potential energy versus low potential energy. Where will things go? That's why this definition sort of encodes just one more bit. So I will write the alternative definition in here, maybe energy stored due to location. For example, a ball being pushed up a hill or being on top of a hill after being pushed up will have large positive potential energy. In our galaxy definition, this corresponds to you really had to work against what the ball was naturally trying to do, roll down the hill, in order to get it up the hill. Okay, so if we have a hill here, that's a very crude hill, and a ball, the ball likes being here. Gravity continually tries to push it back down to the hill. or to the bottom of the hill, and it hates being here. Again, because the gravity force is trying to continually push it down the hill. You have to stuff more and more energy into the ball to work it up the hill. And finally, when it's at the top, that's at the absolute worst place. You've had to punch so much energy into it that it quote unquote hates being there. And if you let it go, it will try and cash in that energy and roll away towards the low potential energy. Now, again, what this means is that, oops, I shouldn't draw a line. Here, at the top of a hill, a bowling ball has high potential energy, for example, 10,000 joules, and here it has low potential energy. Depending on where you set your reference point, you might call this 0. You could call it something less than 10,000 joules. But anyway, the important thing is that here is the high potential energy area. Here is the low potential energy area. And the natural forces that you were fighting to get it between them will try and push you in this direction. Okay? This is the thing to take away from all of physics if you don't take anything else away. This is the core concept. Things hate being in places with high potential energy, and as whatever force you have to fight to get them there, it will try and push you out towards low potential energy if given the chance. Okay? Again, this is a supremely important thing. So much so that I've used the galaxy pen not just for a phrase, but for an entire diagram, if that tells you anything. Okay, in the context of electric charges then, let's do some examples of potential energy. Where are areas where things feel high potential energy versus low potential energy? So let's start here with a fixed positive charge. And we're going to ask what happens to certain particles as they come near this positive charge. Let's bring another positive charge into the picture. We'll call this our test particle. And we're going to ask, where does it absolutely hate being? So where does it you really have to work to push it to be to this place. It doesn't like being there. Where would that be? Would it be over towards the right here before I've brought it onto the screen? Or would it be as you get it closer and closer to the positive charge? Does it hate being there? Is it trying to get away from there? Think about that for 1 second. Where does this positive charge hate being? Right, so since positive charges, like charges, will repel each other, we know that it hates being here. So I'll call this a proton probably by accident eventually, so I'll just call it a proton now. The proton hates being here. And what do we know about potential energy in places where things hate being? Well, it's big and positive there. So PE is large here. Okay? Conversely, where does it prefer being relative to there? It probably it's more enjoyable for it to be over here because it's further away from the other positive charge. It's less stressed to be there. So proton is cool with you. Now it'll still get pushed, but it'll only get pushed a little bit. Relative to here, it'll get pushed a lot. So here, we'll say it has PE is smaller. Okay? It's a very, very important example, and it's actually pretty much the one we're going to be doing all day today. It has a lot of intricacies and different ways to phrase it, for example, with electric fields and voltage, but it all comes back to this picture. So really get this, or keep this one in your head. Okay. Now, I just want to point out something. The potential energy felt by the proton is large. Whenever you're talking about potential energy, and I'll rewrite this later when I have something to compare it to, you're always talking about the potential energy a specific object feels. So it always refers to a specific object and I'll call how stressed that object is to be wherever. Okay, so it doesn't make sense to ask what is the potential energy here unless I tell you what's the potential energy of a positive charge placed here. You can't ask about the potential energy at a random point in space. You can only ask what is the potential energy felt by this object at this point in space, okay? So I'm just going to underline this. It always refers to a specific object and how stressed that specific object is to be in different places. And again, this will be very important later. I know in Physics 1 this was pretty obvious, but electric field is, or voltage, is almost identical to this, but with a twist. You can just ask about the voltage at a place in space. You don't have to specify what. So there's going to be a difference here, so keep this in mind. Okay, conversely, let's do this question. We have a positive source charge pinned in place, and we're going to bring an electron near it. Let's ask, where does an electron love being versus where does it, relatively speaking, hate being? So let's think. Where does the electron like to be? Does it like to be here, close to the positive charge? Or here, far away? Where would it naturally get pulled towards? That's where it likes being. Let's think for a second here. Again, where does it like being? And where does it not like being? Where does it naturally get pulled towards? That's where it likes to be. Where do you have to work to get it over to? Maybe you have to pull it away from something. That's where it hates being. Okay, so the answer would be that the electron likes being here. And the electron hates being here. Oops, I shouldn't. So that means that right out here, the electron, I'm going to write it with an E superscript minus, like in chemistry. The electron has high positive PE here. Or at the very, I should actually comment this, it's higher than in other places, higher than when it's close. Potential energy is always about where do you hate being relative to other places. There's no absolute concept of potential energy. Same as when in Physics 1 maybe you were taught about you can call the bottom of a hill 0 or whatever you want, so you can shift things. Same thing applies here. I won't get into it too much, but it's all about comparing neighboring potential energies for our purposes, so don't worry about it too much. So the potential energy is high positive out here. Again, because the electron does not like being out there. It would rather be getting sucked in towards the positive charge. So the electron has lower PE here. Okay, again, notice I'm specifying the electron feels this sort of potential energy here. Okay, now we're going to make the jump into the object-independent things. So instead of forces, we're going to talk about electric fields, and instead of potential energies, we're going to talk about voltages. This is all going to be about this what object am I talking about question or not. So let's hop into electric field. Okay, so the definition of electric field, I'm going to put it in Galaxy Pen as well because this is a very, very important concept. It's all throughout Physics 2. It's electric field points where a positive charge would get pushed. Okay. Now notice the definition of electric field specifies you're going to be talking about this object all the time. You imagine a positive charge is put in here. What direction is the push? Okay? For instance, if I have a positive charge pinned down here, again, that just means it's like a source charge. It's not moving. It's just creating a field. And again, if I were to put a positive charge here, what direction would it be pushed? To the left or to the right? It would be to the right, right? Because the two identical sign charges don't like being near each other. This one would get pushed away. Therefore, we can say that the electric field here points in that direction. Again, the two complementary viewpoints are positive charge feels a force to the right. That's one viewpoint where the object is specified by you in your sentence. The other viewpoint is the electric field points to the right. Right? It doesn't mention what object we're talking about because implicitly in the definition of electric field, you know that electric field tells you what direction would a positive charge get pushed in this scenario. So the answer would be that the electric field points to the right over here. Okay? And it also points to the right here because no matter where you are, the positive charge would get pushed away from the center, or from this big guy right here. If you were to draw it in other directions, you could imagine, what if this were a 2D problem? A positive charge here would get pushed downwards away from the other charge. So the electric field, which tells you what direction would a positive charge get pushed, draw the arrow in that direction. That's what the electric field is. That definition tells you the electric field points down in that direction. And if you just remember that the positive charges always point or get pushed radially away from each other, you get this nice circular diagram of the electric field around this test charge. Okay? Just a side note here, guys. This positive charge, you don't view it as creating any electric field when you're trying to figure out what the electric field is. It's just almost like an imaginary thing where you would imagine if it were in there, just experiencing things, not creating anything, just experiencing things. What direction would it get pushed? Okay? So again, this is an imaginary guy right here. This is the guy creating the electric field, and this is what you call a test charge. You just imagine how it would flow. It doesn't create anything. Okay? Awesome. Now, what I want to do now is to do a similar diagram for a negative charge. Okay. We're going to ask the question, how does the electric field look in this region out here? Is it pointing to the right or to the left? So again, we remember rather, the definition of electric field is what direction would a positive charge get pushed in if we were to pop it into this scenario. So if I were to pop a positive charge here, what direction would it get pulled or pushed? It would probably get pulled to the left because it likes going near opposite charges. And that tells us, since again electric field just tells us what would a positive charge do, it tells us that the electric field points inwards towards the electron, or whatever negative test charge this is. Okay? Awesome. Now, at this point, it's worth thinking about using the electric field to find what charges would do rather than the other way around. Up until now, we've been putting in charges, positive charges, asking what electric field is there then, using them as sort of stepping stones. Now what we're going to do is we're going to just have the picture of the electric field here, and we'll ask, what would a positive charge do if I put it in this electric field? Okay? So let's pretend we didn't derive it using positive charges. Let's pretend we just were told, here's an electric field. Now, you might not know what's creating it. You might be able to tell what sign of charges are creating it, and we'll use that as a crutch. Not even as a crutch, as a very useful tool. So if I say just here's an electric field, I'll tell you what's creating it. It's a positive charge. And I want to ask you, what would a positive charge placed here do? Would it move to the right or left? Now, for a positive charge, it's pretty easy because we just remember that the electric field points in the direction that a positive charge would get pushed. So the answer is that the positive charge would get pushed to the right. Again, that's because the electric field tells you what direction would a positive charge get pushed. Now, conversely, if I put a negative charge here, firstly, let's look at it as being due to this charge, right? This charge is what is creating this electric field. If I erase all the field lines and my previous question, and I put a negative charge here, what happens? It's going to go towards the proton or the positive charge because opposite charges attract. Now, the electric field points to the right in this direction. But the electron moves backwards, we know, because the electron wants to go towards the positive charge. How can we see that from just the electric field arrows? So how can we understand why the electron moves left, even though the arrows are pointing to the right? And the answer is because, conveniently, positive and negative charges they get pushed in opposite directions always. If you were to put them into the same place. So if I were to put a positive charge here, let me finish writing this first. Right? If I were to put a positive charge here, it rides the electric field out to the right because it wants to get away from the positive charge creating the electric field. Now, again, the reason it wants to go to the right, if I just gave you electric field, is it's probably because a positive charge were creating the electric field in the first place. Conversely, a negative charge placed in a field that points to the right, remember that a field pointing to the right is probably created by a positive charge placed here. So the negative charge will naturally want to move left towards where the positive charge wanted to get away from, right? Because positive charges hate being near positive charges, but electrons love being there, and vice versa. They hate and love being in the opposite places of each other. So electrons or negatively charged particles will be pushed opposite the electric field for this reason. Okay, I'm going to write this in Galaxy Pen. Electrons / negative charges get pushed opposite to the electric field lines. Okay? Now again, this is not really intuitive the first time you look at it, right? Because you see arrows pointing to the right, and you think everything should follow to the right. But remember, those are not the arrows of force. Those are the arrows of, quote unquote, what would a positive charge do? And we know that negative charges will always do the opposite of what positive charges do when it comes to moving, or where they want to be versus hate to be. So negative charges and electrons will move / get pushed opposite the direction of the electric field, okay? Now, we will see this in equation form later. It's not that you have to always be 100% on your toes for this. This is automatically encoded into equations. Using minus signs. However, they can be very pesky to think about. If you just only rely on the equations. In practice, I often do calculations only using the magnitude of, let's say, forces and stuff. And then at the very end, I'll ask, based on the picture, should it go left or right? And then I'll just insert the minus sign at the end if I need to. Okay? At the very least, it's awesome to have as a consistency / safety check to check if your math has gone right or potentially gone wrong. Okay? Now, I just want to point out one more thing again. I've said it before in this. Force refers to the force felt by a particle / the direction a particle will move. Electric field removes that particle information, and it just asks, what would a positive charge do if we put it here? And then just by inference, knowing that negative charges move opposite to positive charges, we know what any charge would do. We know which direction a negative charge would move as well. So the electric field sort of saves you the trouble of having to describe every case separately. And just using your knowledge of negative charges move oppositely, it encodes it all into one diagram. All right, great, guys. If you've made it here with even a vague sense of why electric field and force direction are different or can be different for negative charges, then excellent job. All right, next thing we're going to do is we're going to move on to voltage / electric potential. Okay, now, first comment is that this name sucks. Sad face. Because electric potential and potential energy are not the same thing. Electric potential is aka voltage, is not the same thing as potential energy. And this is a very sad naming convention because the only mistake is you might forget a minus sign and then you get the whole problem wrong. So throughout this, I'm going to use the phrase voltage. You will hear people say electric potential or sometimes even just potential, which is even more confusing. Always be sure if you're talking about potential energy or voltage when you're dealing with ambiguous terms. It will save you. So I'm going to use voltage throughout this. Okay, now for the last section, we sort of compared and contrasted force versus electric field. And the whole key to the difference was that here, that electric fields point where, and then it included this special term where positive charges specifically would get pushed. Basically, voltage is going to do the same thing, just for potential energy. Okay, so here, when we were doing potential energy earlier, we were talking about where do positive charges like being? Where do positive charges hate being? And then from that, we wrote these identifications that the proton's potential energy over here, the proton's potential energy is big here, small here. Conversely, we found that in those same places, in the same situation, the electron had low potential energy, where the proton had high potential energy, which is kind of strange, but it makes sense. The electron likes being where the proton hates being. So we're going to basically have the same deal with electric field here with voltage. So I'll write this in Galaxy Pen because it's important. Voltage is, roughly speaking, where would a positive charge hate being? And specifically, this is like positive / large positive voltage. Okay, so as an example, let's go back to our case of of the lone positive test charge creating an electric field. So positive charges, they hate being right here. So that means voltage is big positive. Conversely, compared to being over here, they love being over here. They would rather be over here by a mile. So voltage, I'm going to say it's smaller. You could potentially call it negative, but we're just going to say it's smaller than it was over to the left. Okay, and again, the reason why we're able to say voltage is we're asking where does a positive charge specifically hate being located. It's also true to say that the potential energy of the positive charge is large here and small here. But again, just like electric field, we were able to tell what the electric field wanted because we were using a positive charge at the beginning. We're also able to just immediately say, oh, a positive charge hates being here? Well, yes, that does mean the potential energy is high here, but the definition of voltage is it's big where positive charges hate being. So the positive charge hates being here, close to the other test charge, or the pin charge. Then therefore the voltage is a big positive number in this area off to the left, and it's a smaller number off to the right. Again, because we're considering how would a test positive charge respond. Now, the opposite case is what would an electron like doing? Okay. Well, obviously an electron likes being here and hates being here. Okay. Oops, sorry, I shouldn't write that. Negative. It loves being here and it hates being out here. Right? It would rather be over near the proton. So, yes, the electron's potential energy is high here, and its potential energy is low. But does that mean its voltage is high here? Right. Are we allowed to use an electron to tell if a voltage is high or low? No. Voltage requires you ask what would a positive charge, where would a positive charge hate being? Again, the analogy here is that for the electric field example, we drew the electric field by asking what would a positive charge do? We didn't ask about negative charges. We just know they would afterwards behave oppositely. We just pop in a positive charge, see what happens, and say, that's the electric field. Here, same deal. We're just going to pop in a positive test charge, record where it loves and hates being, and then that is the answer for what the voltage is. Now, of course, wherever the proton test charge hates being, the electron test charge loves being, right? But there's no issue with that. The voltage only tells us where do positive charges hate being, and the answer for the electrons loving / hating being places, so the electron's potential energy will always be opposite what the proton's potential energy is, okay? Excellent. At this point, I'm going to do a sort of mega example. This is a tested mega example. There's a ton of different parts to it. So I'm going to draw you a picture. We're going to do some questions of which direction will the electric field point, which directions would an electron get pushed / pulled, what's the voltage, where's the voltage high and low, and we're going to go through that now. All right. So oops, I can't highlight that. We're going to have a mega example before we move on to the actual quantitative part, and there will be more standard examples that you'd see in like a problem set. Okay, so the mega example, I'm going to draw it off here. We're going to have 2 plates, and we're only going to be interested in what's happening in the space in between them. I'm going to pop a bunch of positive charges on this plate and a bunch of negative charges. Now these are just fixed charges, they're not moving. We're going to be asking what happens to stuff when I put it in the middle, okay? So question 1 is going to be, if a positive charge is placed in the middle, which direction does it get pushed? I'm going to use super abbreviation here to write on the left. Right? If I were to put a positive charge in the middle, what direction would it get pushed? Now, answer to this is going to be, and by the way, guys, feel free to pause before these questions to try and answer them yourselves. I would really, really encourage you to do that. I use this specific example with my students, and that's how I had them do it, and it kind of revealed if you had a misunderstanding by having you to try it first. So if you want to do that, feel free to. If not, you can keep on watching. All right, so first question is going to be, which direction would this charge get pushed? Well, this positive test charge, it hates being near the positive charges, and it loves being near the negative charges on the right. So on both counts, the push is going to be over to the right, so it's pushed to the right. Second question. If I put a negative charge in the middle, which direction will it get pushed? Think about it for a second here. Again, this is just using, not thinking about electric field too much. What charges are creating repulsion for what charges? A negative charge placed in the middle. Let's see, it loves being near the positive guys, and it hates being near the negative guys. So it's definitely pushed to the left. Okay. Third one, and this is the first tricky one. What direction is the electric field in the middle? Does it point right or left? Okay, let's scroll up to our definition of electric field and check. Oops, I'm too far. Now, electric field is going to point in whatever direction a positive charge would get pushed if I were to pop it in. So we already know that a positive charge would get pushed to the right. So an electric field is going to get pushed, or electric field points where the positive charge would get pushed. So that means the electric field is to the right. Excellent. So the electric field points like that. Now, as a side question here, let's wonder, does it make sense that the negative charge moves against the electric field? Well, yeah, absolutely. If you want to view it as the charges creating the electric field, the electron, of course, as we answered in number 2, hates being next to the negative guys, and it loves being near the positive guys. So, of course, it wants to go to the left. If you choose to view it just from the electric field arrows, pretending to not know what created them, you know that the positive charge would ride the arrows to the right, and negative charges behave oppositely to the positive charges. So the electron would ride oppositely and get pushed to the left by whatever is creating the field. So it does make sense that the two are getting pushed in opposite directions. Great. Okay. Step 4, or problem number 4. What is the potential energy again, not the electric potential slash voltage, but what is the potential energy of a positive charge put here, right in this spot? Okay. Is it large or small? Positive. So again, that means does it hate being there or like being there? Okay, well, it's stuffed really close to positive charges, so it doesn't like being there because the positive charges are trying to push it away. So it's a pretty large number there. All right, similar example, or similar question. What if I put the charge here instead, the positive charge there? Does it like being there or hate being there? And does that mean it has large or small potential energy? Okay, it would like being there because it's near the minus and far away from the pluses that it hates near being. So this is going to be a rather small number for potential energy. Okay, let's do another example. What is the potential energy of this time a negative charge put on the left side? So for example, in this hole out to the left here. Oops. Okay. A negative charge placed there, does it like being there or hate being there? Okay, well, it's near positive charges, so it definitely likes that. And it's also far away from the electric or from the negative charges that are repelling it. So it really likes being there, so it's a small number on the left. All right, what about the potential energy of an electric charge or an electron placed over on the right side? Is it large or small? Let's see, does it like being there or hate being there? Well, it's stuffed right next to other negative charges, so it absolutely hates being there. So that means it has a large potential energy being there. All right, 2 more questions, and then we'll be good. I'm actually going to redraw the diagram down here. Again, these are the electric field lines. Where is voltage large? Okay, now remember, what is the definition of voltage? It's like potential energy, but for a positive test charge. So where would a positive charge hate being? That's where voltage is big. So where do positive charges hate being in this diagram? Over to the left. They hate being next to the other positive charges. So the voltage is large anywhere on the left. Next question would be, where is the voltage small? Now again, small voltage means the positive charge. You're always doing positive charge with voltage. Where does it like being? Well, it likes being near, positive charges like being near other negative charges. So voltage is small over on the right. Excellent. This is every question you could be asked about the direction of things moving here. Only possible spin would be, let's say I told you the voltage and you didn't know that these charges were here creating anything. So suppose I only tell you voltage is large on the left and small on the right. And then I ask you, where does where does a positive charge, and then a separate question, negative charge, like being? Okay? Well, a positive charge, remembering the definition of voltage, positive charges hate being near large voltage, and they love being at small voltage. So the positive charge loves being at the small voltage, which is on the right. Again, voltage, we built the voltage description based off of asking where does a positive charge like versus hate being. So of course it loves being where the voltage is small. That's how we, at first time, knew that the voltage was small. That's how we calculated if it was small or big. Now, this one could be tricky. Where does a negative charge like being? Remember, voltage only tells you where do positive charges like or hate being. Negative charges are always going to behave oppositely to the positive charges. You can sort of view that as they respond oppositely to the charges creating the voltage, or you can view it just as they respond oppositely to field lines / voltage hills. So the electron likes being where protons hate being, and protons hate being on the left, where the voltage is large. So the electron loves being on the left. And again, the way we told that is that voltage tells us where protons hate being when it's large. So protons hate being on the left, and electrons respond oppositely to fields, pushes, liking versus hating being places compared to the protons. So the electrons love it where the protons hate it. Let me quickly think if I can... Yeah, okay. One more potential question, haha, no pun intended, is, again, suppose I only told you the voltage thing. Suppose only know voltage. Which direction does a proton get pushed? Okay. Which direction will it get pushed? Okay, we know the voltage is high here, and the voltage is low here. We know things hate being near high voltage, and they love being near low voltage, and the forces push them from high voltage to low voltage. And so then we see it would get pushed to the right, which is in agreement with the electric field direction. You can almost view the electric field as pointing towards low voltage, right? Because voltage being low means things like being there, and things get pushed from high voltage to low voltage. This is just like how, again, on a hill, okay, that is the worst hill in the history of mankind. There we go. Things get pushed by the gravitational field / force down a hill towards low potential energy. So positive charges, and voltage tells you exactly where they like / hate being, get pushed from high voltage to low voltage, which is in agreement with the direction of the electric field. It is all constructed in a consistent circle. If you choose to do it the electric field way, you're good. If you choose to do the high to low voltage way, you're also good. All right, last question is going to be, same information, where does a negative charge get pushed? This will be the most difficult question. Okay, and again, if we only know the voltages, where does the electron hate being versus like being? Okay, well, the protons like being here, so the electron hates, or sorry, other way around. The protons hate being here because the voltage is high here. So protons hate here. That means electrons like it here. Again, purely because we're told the voltage is high on the left. And then conversely, the protons love being over here, so the electrons hate it. So the electrons will get pushed away from the place they hate over to the left towards the point they like. So the electron will get pushed from the low voltage to the high voltage. It gets pushed from the right to the left. And again, this push is from low voltage to high voltage. And again, that doesn't bother us. Things get pushed from high potential energy to low potential energy. And for an electron, low voltage is high potential energy. Again, because low voltage means positive charges like it here. So electrons hate it here. So this is all consistent, and we haven't done anything wrong. We haven't messed our signs up. Guys, if you got through that example, even if it takes you a couple of times, if you can get all these and really understand like everything in a consistent setup, you're going to be golden with this. All right, for the next part of the video, I'd advise you take a small break, stretch out or something. This is a lot to take in. Maybe even watch the next part of the video another day. We're going to cover it's just 2 or 3 equations that actually work this into equations. Fortunately, the equations are much easier than this. It's going to be pretty much plugging and chugging in. So we'll make a return to that in the next half of this video. All right, I'll see you soon, guys.